All right, so what we're going to do this video is actually use character tables, or actually show where some of the characters come from. So the first thing we want to do is we're going to look at a molecule which has a point group symmetry of C2V. C2V has the identity, the do-nothing operation. It has an axis of rotation of 180 degrees, and it has a vertical plane in the XZ plane and a vertical mirror plane in the YZ plane. So let's just draw a typical molecule. NO2. And we're going to look at the p orbitals on the nitrogen, which is in the center. All right, so the C2 axis is this way, and we're going to put the molecule, and it's the Z axis. I'm going to put the molecule in the YZ plane. It turns out you actually get different answers if you put the molecule in the XZ plane or the YZ plane. And that will affect the labels B1 and B2, which will change. This is a real problem in the research literature. If somebody uses, C2V point group symmetry, they put it in the YZ plane, somebody else puts it in the XZ plane. There's a lot of confusion about these particular two entries in the character table. All right, so what we're going to do is introduce an idea of an operation, and then we're going to represent it by a matrix. All right, so we're going to create a vector of the p orbitals on the nitrogen atom. And this is just a set of the p orbitals, and we're going to say, let's do nothing on that, and the result is the same vector. Okay. The px orbital becomes the px orbital, py stays the py, pz stays the pz. And so we ask ourselves, what matrix, if we multiply it by this vector, gives the same vector? And the answer is the identity matrix. All right, so we're going to write down the identity matrix as a 3 by 3 matrix. Like that. So if we multiply this vector times this matrix, we'll get this thing back. Okay, now the character is the sum of the diagonal elements of a matrix representation of the symmetry operator. So you choose a set of functions, that's called your basis. Once you choose that, you see what the effect is from all the symmetry operations, and then you try to derive a matrix that does the same operation. And the sum of the diagonals is the character of this matrix. So this is higher math. The character, which is denoted by the letter chi, is 3. All right, so we're going to repeat this process for the other 3 symmetry operations. Okay, but this time we'll actually get some changes, so it won't be simply just doing nothing. All right, so let's look at the C2 axis rotation. So if I have a py orbital, okay, that's the p orbital along the y-axis, and I rotate 180 degrees, so I'm going to do the C2 rotation of this, and I'm going to get this one. All right, so it stayed on the same center, but it has moved. All right, and so we're going to take a py, and it becomes a minus py. So it's not quite, it's not moving, it's not turning into a px or a pz, but it's just changing sign. All right, so we continue that with the other 2 orbitals. The C2 operation on the pz orbital just leads to the pz orbital. Because the pz orbital is up and down, we rotate, nothing changes. The lobes stay put where they are. And then finally, the C2 operator applied to the px. Okay, so the px orbital is coming in and out at you. If we rotate that 180 degrees, you can see if the tip of the marker is the positive end of the orbital, we rotate 180 degrees, we now have the negative end of the orbital at you. So it also changes sign as we do the rotation. All right, so the matrix that will do this, it'll change the sign of y, it'll change the sign of x, and leave the sign of the pz orbital unchanged. That matrix will be the C2, and it'll be -1, 0, 0, -1 here, 0, 0, 0, 0, and +1. So the character of this one is -1. Okay. Now we can repeat this analysis for sigma v. All right. So I'm going to sit down and figure out sigma v. All right. I'm going to let them do sigma v and sigma v prime. During multiple edits, I have figured out what the matrix representation is for sigma v and sigma v prime. And it is these two matrices here. Okay, and so we're going to go ahead and add the diagonal elements to get the characters. So chi equals 3, chi equals -1, chi equals 1 for this one, and chi equals 1 for that one. Okay, now the next thing to notice is that these three matrices are all perfectly diagonal, which means you cannot make them any more diagonal than they are. And so these matrices are irreducible. Okay, so we're going to take a look at the entries for every one. We're going to look at the entries for Px. We have 1 for E, so it could be any one of these four. Then we have a -1 for a C2, so it could be this guy or it could be that guy, but it can't be these two. Sigma V of 1, and so it's B1, right? So the last one, it better be a -1. There. Fixed. All right, this is actually the matrix. All right, and so how do I know that I finally got it right after multiple edits? It's because that's right there. Okay? So let's look at the entries for y, and guess what we're going to get? We're going to get 1, -1, -1, 1. Let's look and see if I did it right. 1, -1, -1, 1. Yay. All right, and then finally for z, 1, 1, 1, 1. So z is an A1 irreducible representation type. It's that. Okay, so this is one application actually of these things that appear on the side of the character table. It says, what is the irreducible representation of individual px or py or pz orbitals on a central atom? Now we can't do this for the oxygens. It's a little more complicated. But we could actually say something about the d orbitals on a nitrogen atom if we were using them. The dyz would be a B2 type. The dxz orbital would be a B1 type. The dxy would be an A2 type. And then the x squared minus y squared and the z squareds would be A1 types. Okay, but that's the meaning of a character in point group analysis. All right. The next video, we're going to show you how to break this down and show that the combination, the characters only, are 3, -1, 1, and 1.